Okay, we're starting 7.3. I'm going to run through the investigation very, very quickly. So if you have a protractor, that's great. If you don't, just pay attention and or pay attention to the person next to you who has a protractor. So we've got Corey. Corey's going to install wheelchair ramps at his high school. Not all locations have the same vertical climb, though, right? Sometimes you might be going up 2 steps. Sometimes you might have to go up 10 steps, whatever it is, okay? Maybe it's a hill and there's no steps yet at all. Okay, so he wants all of the wheelchair ramps to have a slope of 1/12. All of the wheelchair ramps to have a slope of 1/12. What can you tell me about slope?
I remember this. Rise over run.
Rise over run. So if he's saying that they're going to have a slope of 1/12, that means they're only going to go up 1 as they go over 12. And then that is a safe wheelchair ramp. Okay, a 1/12 ratio is a good wheelchair ramp. Okay, and again, that can go any direction. It could be any size. If it were too tall, right, then it would have to be 24 long. And then you'd have the same ratio. That makes sense to everybody?
Yeah.
All right, good. Carrying on. So the investigation says draw 3 similar right triangles. 3 similar right triangles, all with a slope angle of 15 degrees. What is a slope angle? Well, I'm going to draw my triangles, okay? I'm going to put a vertex there on the edge, and then 15 degrees basically just means I'm coming out here to 15 and putting a dot. Okay, now that's not quite a right triangle, so I got to actually bring that dot over a little bit. And if I finish that triangle out, I'll have a right angle here, and this angle here will be 15 degrees. Okay, so that's one. That's one. I'm going to draw another one, and this time it's going to be a bit longer.
Are we supposed to be drawing this on a brick right now?
Yes.
If you have a protractor, then yes. I'm going to make this one a bit bigger. It's going to look like this and like that. And we'll get a right angle somewhere over here, and then I'll just erase whatever's extra. That worked out pretty good. Okay, and this angle is 15 degrees. Okay, I'm only going to draw 2. We'll do the work with 2. If you drew 1 or 2, that's a good idea. Okay, all you have to do is make sure that this angle is approximately 15 degrees. The closer to 15 degrees, the more likely this will work out. Now, what we're diving into, so we've already talked about ratios within triangles and similar triangles. Now, I have similar triangles, okay? I have a right angle triangle in both cases, and I know that the slope angle is 15 degrees in both cases. So I have similar triangles, okay? So every single right angle triangle with an angle of 15 degrees is a similar triangle. So what do we know about the ratios of sides within those triangles? They're going to be equal. Okay, that's what we learned about in similar triangles, that if I take side A over side B here, and I calculate the ratio, and I take side A and side B here, calculate the ratio, then I'm going to get the same ratio. I'm going to get the same number. Okay, I'm going to erase that for a second. We're going to keep that in mind. Hopefully you're building on what you already know. And we're going to come back to that. So let's call this triangle A. Let's call this triangle B. And you have a little diagram, you have a little table at the bottom. Okay, let's talk about triangle A. The slope angle is 15 degrees. Triangle B, the slope angle is also 15 degrees. And now I need to get out my ruler because we're going to do some measuring. So now I need the rise. We're looking at triangle A. The rise here is, I've got almost exactly 2, so that's what I'm going to write. And the run is 8. Wow, how convenient is that? I guess I did just copy my protractor. So, okay, so I've got a rise of 2 and a run of 8. So what is my slope? Rise over run. 1/4. Okay, don't mix them up just because you like putting the bigger number on top. Please don't do that. So for triangle A, the slope is 1/4. What do you think I'm going to get for the slope of triangle B?
1/4.
Even though it's a bigger triangle?
Yeah.
It has a bigger run and a bigger rise? Okay, let's find out. So triangle B, let's look at the rise. 3, almost exactly. And the run, nice. 12, how convenient to accidentally get whole numbers. And then rise over run, 1/4.
Wow.
Oh, so the slope is the same in both cases. Now remember, the slope is a ratio. The slope is a ratio of the rise over the run. Please pay attention. We're going to learn how to name the sides in right angle triangles, which you already know. But if we're talking about this angle right here, then we have to name our sides. This side way over here is called the opposite side. Okay? This side is called the adjacent side. Adjacent just means right next to or beside. I don't even know if I'm spelling it right, but hopefully it's close enough. So we have opposite side length over the adjacent side length is the ratio 1/4. Okay? Now what we're going to learn today is that ratio that we just talked about, opposite over adjacent, is called the tangent ratio. Okay? The tangent ratio is opposite over adjacent. Say it another way. The tangent of 15 degrees is equal to the ratio of the opposite side over the adjacent side. So now, do me a favor. Do you have a calculator?
Yeah.
Go ahead and find the buttons kind of top middle that say sine, cos, tan. Sine, cos, tan. So here's my tan button. Okay? Go ahead and type the tangent of 15 and hit enter and see what you get. Okay, I got 0.26 or 0.27, which is really, really close to 1/4. That means my drawing isn't perfect. Okay, the calculator is perfect. The tangent of 15 degrees, the ratio of opposite over adjacent, in a right angle triangle that has an angle of 15 degrees is 0.268 if we rounded it, 0.27. Okay, our estimation was 0.25. So we did pretty good.
Let's go.
But that's the relationship. That's what we're doing today. We're looking at the tangent ratio, which is you look at an angle, you look at its opposite over its adjacent, boom, that's its tangent ratio. Okay, on your next page, the whole thing is blank. I'm going to basically write notes for what we just did orally. Please draw yourself a little right angle triangle, call it ABC, and a larger right angle triangle, call it DEF. And we're going to note that these are similar triangles. Okay, it doesn't necessarily, I can test whether or not they are similar based on their ratios. So let's find out. We're talking about, and somebody asked a question earlier that I'm going to address too. So if we're looking from, in the little triangle, angle C, okay, so let's say we're looking from angle C, often the angle in question will be marked by a little arc like this, okay? Then what that tells us is we have an opposite side. That's usually the easiest to identify. And then you're right, there are actually two sides meeting at angle C. So which one do I call adjacent? Well, we know in a right angle triangle that there's one special leg, one special length called the hypotenuse. So always identify the hypotenuse first, and then the other one, the other leg, is called the adjacent side. Okay? And over in our bigger triangle, we're going to look from angle F. That's another good way to think about this. It's kind of like you're standing over here and you're looking at the triangle from the perspective of angle F, which makes, boom, this one opposite. this one hypotenuse, and this one adjacent. And we could do these exact same questions looking at the triangle from angle D. And if we did that, then this would be opposite, and this would be adjacent. Hypotenuse wouldn't change.
But you couldn't look at it from angle even.
It's unnecessary to look at it from angle E because you already know that angle E is 90 degrees. So these relationships that we're learning about deal with the acute angles within a right angle triangle. Yeah, so you're going to look at things from angle F or from angle D, from angle C or from angle A. Those are the acute angles in a right angle triangle. Okay, so what can we say about these side lengths and the ratios between them? Well, if I'm looking at my small triangle here, and I want to talk about the tangent ratio today, so we indicate that by saying the tangent of angle C, the tangent of C, or just tan C, is equal to, it is this ratio, okay? So the tangent is a ratio. And because it's the tangent of C, then I have to use the angles, the side lengths, looking from the perspective of C. Now, the tangent is always going to be the relationship between the opposite side length and the adjacent side length. Always. It's never going to involve the hypotenuse. It's never going to be A over O. It's never going to have H in it. It's always going to be O over A. Okay? And I'll show you a little cheat to help you remember it in a little bit. So in our triangle that we have here, ABC, what is the opposite side length? Well, it's AB. AB is the opposite side length. And the adjacent side length is BC. All right. You try to do that faster than me in the blue triangle, in the bigger triangle. We're looking for the tangent ratio of F. It's a ratio, so I know it's going to be a comparison of two numbers in fraction form. I know it's going to be op over adj, and then I can name those side lengths. That's DE over EF. All right, so I know that these are similar, okay? I'm assuming that angle C is the same as angle F, angle A is the same as angle D. That tells me that these triangles are similar. And so why don't we just note that if triangle ABC is similar to triangle DEF, then what else do we know is true? Well, that means that they're going to have corresponding ratios according to their size. They're going to have equal ratios, using corresponding side lengths. So let's look at what side lengths correspond to each other. If we start with AB over here, what side length in the larger triangle corresponds to AB?
OD.
DE. So the ratio that is made by comparing AB to DE is the same as the ratio that can be built comparing side length BC to EF. Thank you. Okay, we learned that the other day. That's just similar triangles. That's just corresponding side lengths in similar triangles. Now, we also know something else. We now just learned that since we have angle C is the same as angle F, that the tangent of C is actually going to be the same as the tangent of F. Okay, so here we took ratios here from little triangle and big triangle, made a ratio, corresponding sides, and little triangle and big triangle, corresponding sides made a ratio. Now we're going to be looking at the ratio that's created within just this smaller triangle. We said that the tangent of C is AB over BC. AB over BC. And we know the tangent of F is DE over EF. Mr. V, what are you trying to tell me? Okay, now we're going to do some sticky algebra here. What we're going to do is we're going to we're going to divide both sides by BC, and we're going to multiply both sides by DE.
And then we have practice problems.
Okay, and we also know that, so in the concluding statement here is because this is all true and because they're similar triangles, these things are true. This is the ratio that belongs to tan C. It is the tan ratio for C, and this is the tan ratio for F. So we know that tangent of C is equal to the tangent of F. And we already know that they're similar. So it doesn't matter what size the triangle is, as long as that angle is the same, then we know that their ratio is also going to be the same. Okay, so example 1, we're just finding the tangent ratio. I keep saying it that way really clearly and loudly so you understand. Tangent is a ratio. It's a relationship between two different values, two side lengths. So if we've got, can I do it with it here? Yeah, that's going to be nice. Okay, so we're in A. I'll do my work off to the side here. And we want to identify the opposite, adjacent, and hypotenuse for the triangle that we have in A. So you can see it's asking us to look from the perspective of angle theta. So we have an opposite over here, that's 5, and we have an adjacent right here, that's 12. So we're going to just write, we're going to set this thing up. The tangent ratio of angle theta is op over edge. I'm going to work across to save space, which is 5 over 12. And I need to put that in my calculator. And I end up with and we're going to keep, it says correct to 4 decimal places. We want to keep a lot of decimal places when you're determining ratios, okay, because you're going to use those ratios in the rest of the problem usually in order to find out more information or in order to find out what the actual angle theta measures. Remember that what we're getting here is not the measure of angle theta. You're not getting an angle measurement, you're getting a ratio, you're getting a relationship between these two side lengths. So 5 over 12 is 0.4167. And this is essentially just to help you practice putting these things in your calculator and understanding what they mean. Okay, in our next triangle in B, we've got angle theta. So we're going to find out the tangent of theta. We know it's op over adj. Ooh, can you identify the opposite side? 6.8. And the adjacent side, am I going to use 8.2 or 4.5? Why? How do you know?
Because it's not the hypotenuse.
Yeah, 8.2 is across from the right angle, which means it's the hypotenuse. The hypotenuse is always across from the right angle. So we're going to put 4.5 in there and carefully punch that into our calculators, and we'll get a ratio of approximately, and maybe I'll work down here, approximately 1.5111, correct to 4 decimal places. And in C, go ahead and try C on your own and then check back here to see how you did. Set it up the same. Really try to do it on your own.
It's the same one. It's the same, is it not? There's just a 0 in a different corner.
There's not a 0. That's a theta. That's a symbol that tells you which angle you're considering. But I thought we discussed that that changes the opposite and adjacent, doesn't it? So is it the same? It's not the same. It's a totally different angle. It's going to have a different ratio. Okay? So if you need to draw that out, go ahead. But look, here we have opposite over adjacent. Here you have opposite over adjacent. To suggest that those are the same is like saying 3 over 2 equals 2 over 3. Okay? That is not true.
But how do you know that with the
Tells you the angle.
And the placement of theta basically tells you what position you're looking from. You're looking at this triangle from theta. With respect to theta, this is the opposite, and this is adjacent. In triangle B, looking from theta, with respect to theta, this is opposite, and this is adjacent. Okay, heading to example 2. This again is going to be using our calculator. So we found the tangent ratio when we did not know the angle measurement. That was example 1, right? You found the ratio, but you still don't know the measurement of angle theta. You can get it, and we will get to that. Example 2 is basically helping you learn how to put that in your calculator in order to determine a ratio, and then we're going to be able to go backwards to determine the angle, but I'll tell you about that later. So example 2 says evaluate each of the following with a calculator, record your answer, round it to 4 decimal places, the tangent of 25 degrees. Okay, so again, this is like you're in this triangle. That's a terrible example. Okay, you're in this right angle triangle, and you know this angle is 25 degrees. Okay, and you're going to find the tangent ratio for an angle of 25 degrees. So you're finding out the value of opposite over adjacent. Is it going to give you the length of this side? No. Is it going to give you the length of this side? No. It's going to give you the ratio of those two side lengths, even if you don't know the side lengths themselves. Okay? So go ahead and get your calculator out. It's really simple. You press the tan button, you press 25, you hit enter. What do you get?
0.4663.
And watch what I do with my equal sign every time, a dot on top, 0.4663. Okay, B, same thing, tangent of 60 degrees. So now you're looking at a triangle, and it's got a right angle, and you're looking from here, it's about 60 degrees, and you're finding the ratio of opposite over adjacent. All you have to do is put it in your calculator. Tan 60, enter. What do you get?
1.7320.
321. Round to the nearest, in this case, thousandth, 10,000th, I guess, 10,000th. Okay, pretty straightforward. Now you know how to get a ratio when you have the side lengths, and you know how to get the tan ratio when you have the given angle. Okay? And again, with your ratios, you're always going to leave them rounded to 4 decimal places. Before we head off to example 3, you have a little bit of space for notes at the bottom of example 2, just underneath example 2. Okay, so this is what we're going to be talking about. We're going to be talking about inverse operations. Inverse operations. So what is an inverse operation? This is an operation that will undo its inverse. Huh. It's an operation that will undo another operation. So if we think about our operations, what are our basic operations in math?
Addition, subtraction,
Addition.
multiplication, and division.
Addition, subtraction, multiplication, and division. Okay, leave a little bit of space underneath because we're going to add to this list a little bit. And then we have their inverse. Okay, so basically what I'm asking is what operation is going to undo addition?
Subtraction.
Subtraction. So if I had x plus 7 and I wanted to get x by itself, I would have to undo the plus 7 and I'd go x plus 7 minus 7 and I'd be left with just x. Okay? In that way, subtraction undoes addition. What is going to undo subtraction?
Addition.
Addition. Okay? So addition and subtraction are inverse operations. They will undo each other. What about multiplication? What's inverse to multiplication?
Division.
Division. And inverse of division?
Multiplication.
Okay? Division and multiplication are inverse operations. They will undo each other. If you have Megan times 4, and you really actually only want one Megan, you just divide that by 4, and you'll just have one Megan.
You only
Okay?
need 2 Megans.
Yeah. Okay. Now, we can take this further. These are the basic operations of arithmetic. But you also know, for instance, if I take x squared, I'm squaring it. What is the inverse operation of squaring something?
Square root.
Square root something. Okay? So if I take a value and I square it, I can get back to that value by square rooting. The square root will undo the square, and that works both ways. The square will also undo the square root. Now, you have an operation. It's kind of like an operation. It's not exactly an operation, but on your calculator, you can take the tangent of a value. Do you remember what that's talking about? If I take the tangent of a value, what am I actually finding?
You were finding.
Say I'm in my right angle triangle, and I've got angle G here. Okay, and I know the measurement of angle G, and I take the tangent of G.
You are taking.
What am I actually finding?
The opposite angle divided by the adjacent side.
That's confusing. No, it's a ratio of sides. Okay, paying attention. Opposite over adjacent. They're both sides. They're both sides, so no, not what you said. And it's a ratio. That's what you're finding. If you're taking the tangent of G, you're finding the ratio of the opposite side length over the adjacent side length. Now, friends, there is an inverse operation for tangent. It is simply called tan inverse, or the inverse of tan. The symbol
Very.
is this. Superscript -1. It looks like an exponent of -1. That's not what it is. Okay? It indicates inverse. It's simply the operation that will undo the tangent. What does that mean? Well, that means to get from the angle G to the ratio, you take the tan. But if you're given the ratio, you can find the angle by taking tan inverse of that ratio. Does that make sense? Another way to say that is, yeah, well, we'll just leave it at that for now. Tan of an angle will give me a ratio. If I have the ratio and I want the angle, I'm doing it backwards. I need to undo things. I'm going to use the inverse of tan. Another way to say that is if I want just the angle by itself, paying attention, but I have tangent of that angle equals a ratio, watch. What happens when I take the inverse tangent of the tangent of G? These operations will undo each other, and I'll just be left with G. If I take the inverse tan of this side, I also have to take the inverse tan of the ratio, and that I can just pop into my calculator, and I'll get the angle G is a certain measurement, okay? That's probably a little bit confusing right now, but we're going to go through a handful of examples, okay? If you look at example 2, look at what we did, okay? Example 2, we took the tangent of 25 degrees. Okay, this is an angle measurement, which means you're looking at a right angle triangle from, let's just call it F, and you know F is 25 degrees. And you got the ratio of this side length over this side length, okay? The final answer there was approximately 0.4663. And all you had to do was go on your calculator, find the button that says tan, 2, 5, enter, right?
Mhm.
That got you a ratio. Now look at this. If I take the inverse of the ratio, what do you think number will my calculator pop out?
25.
All right, let's see.
Where's 10?
I'm taking, so now to get the inverse, you're going to put second function, tan. You can see the little letters right above your tan button is tan inverse. If you don't have your calculator, shame on you. Go get one right now. And all you're going to do is type in 0.4663 because that's our ratio. Enter, and we get 24.999. Why isn't it exactly 25?
Because it's approximate.
It's approximate because we rounded to 4 decimal places, okay? So you get it back out, it's going to be 25 degrees. Now, we took the inverse tangent of a ratio. Our answer is going to be an angle, okay? Here, we took the tangent, which is a ratio, of the 25 degrees. Our answer is a ratio, okay? This is a comparison of this side length to this side length. And when we undo it, we're going from that comparison back to the angle itself. Okay, so that's a really helpful tool that you need to know. It's the inverse tangent of a ratio will get you an angle. Okay, what do you think would happen in your calculator if you typed this? Just quick trivia. You type tan, inverse tan, and then in the bracket you hit tan of 25. What do you think will come out? Don't do it.
Oh, probably the answer.
If I have 25 and I take the tangent and the inverse tangent, what's going to happen?
Malfunction.
Probably the answer.
Self-destruct.
I think it's going to be the answer.
No.
Anyway, we paused that to, scold our students, but
There.
it comes out as 25 because you're doing something and then you're undoing it. You're just going to be left with what you started with, like multiplying by 7, then dividing by 7. You
I
get
didn't know
the
you had
original,
that
what you
belt.
started with. Here we go, example 3. Example 3, we've got our friend Fiona. She's building a skateboard ramp. She wants the ramp to rise 1 meter and have a horizontal distance of 2 meters.
He's perfect.
Okay, so there's our ramp. It's a 90-degree angle there, we can assume. We've got a 1 meter rise and a 2 meter run. And we want to know at what acute angles should she cut the wood rounded to the nearest degree. So what is that asking us? That's saying, essentially, what is the measurement of angle A? What is the measurement of angle B? Okay? That's all we're finding. And we have 2 measurements. Now, if we look from angle B, I'm going to do it in 2 different colors. If we look from angle B, orange, we have opposite and we have adjacent. If I ever, looking from a certain angle, have the opposite and adjacent, that means I can use the tangent ratio. Okay? Now, in red, what if I'm looking, if I want to find angle A, I have, looking across, opposite and adjacent. If I have both of those side lengths, that means I can make a ratio for those side lengths, which means I can calculate the measurement of angle A. Okay, so let's look at angle A first. We're looking for angle A, and I actually have the tangent ratio. So I know that the tangent ratio of angle A is equal to op over adj. It's the ratio opposite over adjacent. Now I know those measurements. Opposite to angle A is 2 meters. Adjacent to angle A is 1 meter. How come I'm not using this side length?
Because that's a hypotenuse and we don't know it.
So in every right angle triangle, the side length across from the right angle is called the hypotenuse. So whether I'm looking at orange or red, this one is the hypotenuse, and it's not involved in the tangent ratio. There are other ratios that it is involved in. We learn about those in the next lesson, but it's not involved in the tangent ratio. Now, I know that the tangent of A is 2, right? 2 over 1 is 2. Well, how do I find out what just the measurement of angle A is? I have to undo the tangent operation here. It's not really an operation, but we're going to call it that. I have to undo the tangent operation here, which means I have to do the same thing on both sides. So look at what happens. I'm going to do it in a couple of steps that you won't necessarily have to write. But basically what I'm going to do is I'm going to take the inverse tangent of this whole side, and I'm going to take the inverse tangent of this side. What's left over here? Just A, because I took a tan and then undid it. And over here, all I have to do is punch this into my calculator, and I need to make sure I do it carefully. I'm taking the inverse tan, so I'm getting the second function of the tangent button with a 2. I can close the bracket or not. Your calculator will figure it out. Hit enter, and I get 63.4. And we're supposed to identify this to the nearest degree. So because that measurement is approximately 63.4, we're going to give us a final answer of 63 degrees. Okay? Remember, you're going from a ratio, you're finding the angle measurement. Angles are measured in degrees, in grade 10 anyway. And there you have angle A. Okay? Let's go ahead and figure out for angle B. I'm going to let you try to do it on your own. I'll just help you set it up. I'm looking at my orange letters now. So I have the tangent of angle B. The tangent ratio is always opposite over adjacent. So now I have 1/2 on the right side. If the tangent of B is 1/2, then the measure of angle B is the inverse tangent of 1/2. And you can, in your calculator, it's probably easier to put 1/2 as a decimal. What's 1/2 as a decimal? 0.5. Okay, so go ahead and just do inverse tangent of 0.5. And you should end up with angle B is approximately, to the nearest degree,
27
27 what?
degrees.
27 degrees, don't forget it. If your calculator didn't do that, then it's also possible that your calculator is not set to degree mode. There are 3 ways of measuring angles on your calculator. So if it's not set to measure them in degrees, you might have gotten a funny other number. But if it is set to degrees, then you would have gotten 26.56, which we would have rounded up. If you don't have this calculator with you today, make sure you have it tomorrow. Okay? Or ask to borrow. Good. And yeah. Question for you. Did we have to do this process to find angle B after we already found angle A?
No,
No.
Why not?
I have no idea, but you would ask the question if there was another way.
What could we have used?
We could have used
Triangles and 3 1.
Yeah, we could have used what's called algebraic reasoning. We could have used algebraic reasoning to calculate the measure of angle B after finding the measure of angle A. By the way, this little symbol means the measure of, the measurement of, okay? So this is angle A. This is the measure of angle A, or at least that's how I use them, okay? So use symbols when you can. You don't need to write full-length sentences. If a symbol will do just fine and communicate it, but then you have to know what those symbols mean. So what could we have done? We could have said angle B equals, well, I know this is a 90-degree angle, so I'm in a right angle triangle. ABC added up, the sum A plus B plus C is 180. But I don't need to worry. I can just take off 90 right away. And I can say B is 90 minus A. 90 minus 63 is 27 degrees. Okay? When you're doing your math work, you don't need to write the degree sign in everywhere, but please do make sure that it's in your final answer. Because this is a word problem, we should wrap it up with a statement. Fiona should use angles of approximately 63 degrees and 27 degrees. Okay, example 4. So example 4, we're going to be using the tangent ratio again, okay? And just, I'm going to put it up here right at the top of our example here. We've got the tangent of, let's just call it A. That's any angle. By the way, angles are always capital letters. Just like on a Cartesian grid, vertices or points are always capital letters. Angles are capital letters. Side lengths, lowercase. Yeah? Side lengths, lowercase. Corners, angles, capitals. Okay? So we know the tangent of A is look at the triangle from the position of A, and you're looking at opposite over adjacent. So keep that in mind. You have a triangle drawn for you there. It looks a little bit different, but it's actually still a right angle triangle. They just threw the right angle at the top part. Okay? It's labeled side length X, 9.2, and you're told this angle is 28 degrees. Now, who can tell me what's different about this example? Why is this slightly more challenging?
We don't have one of the side lengths.
We're missing a side length, which means we're missing the ratio. We don't have the full ratio, okay? But we do have the measurement of the angle, okay? So we can actually use the tangent ratio here to determine the exact length of X. We just happen to be missing different information than usual, okay? So here's what's happening here. We're looking from the given angle, okay? So pay attention. You're always going to be looking from the given angle. If they give you an angle, you're like, sweet, that's lots of information. That's where I'm going to be looking at the triangle from. How do I identify the names of my sides if I'm looking from 28? What is the side X? Opposite. And 9.2? And this side here? Hypotenuse, because it's across from the right angle. All right, let's just plug in what I know. Remember, this is the measurement of angle A. So I'm taking the tangent of 28. Common mistake that students make right here. They say, oh, 28, this whole side is just 28. No. 28 is A. Just put it where A is. Tangent of A, tangent of 28. Okay, good. Next, opposite, I don't know. It's X. Leave it as X. Adjacent, I do know. It's 9.2. From here, it's just your simple basic algebra skills. There's nothing new in how to solve this, okay? Don't be thrown off by this. Just think of this as one entity, one chunk together, and we're looking for the side length X. How do I solve for X?
You multiply.
Right now, X is being divided by 9.2. So I'm going to undo that by multiplying by 9.2. If I do it to the right-hand side, I have to do it to the left-hand side. Okay? Over here, what happens? They cross off, leaving me with just X. Over here, it's not difficult, okay? You can do this a couple different ways, but your calculator is smart enough that if you actually just type 9.2 tan 28, I don't know if you can see that, but right there, 9.2 tangent of 28, enter, boom.
Yeah, I got it.
Okay, it will pop out an answer. The answer is 4.9 to the nearest tenth. Okay, 4.9, that's approximate. And we'd typically swap these as a final answer. We'd put this over here, and we'd make sure we note that it's measured in centimeters. Okay, basic algebra skills. What else could you do in your calculator? You could put this in, tan of 28, hit enter, then hit multiply, 9.2, enter. Okay, that'll get you the same answer if you like doing it step by step. But that's what that looks like. Let's head to example 5. Okay, I'm going to clear this. Example 5. Solve a multi-step problem using the tangent ratio. We've got a radio transmitter. It's going to be supported by a guy wire as shown. All right, we've got a right angle triangle. Here's our tower. We've got a wire coming down to the ground. It's making a 65-degree angle with the ground. And we're told that the wire is going to reach the tower at a height of 30 meters. Okay, so we've translated our algebra into a diagram. And what are we trying to find out? The wire can be ordered in whole number lengths of meters. How much wire should be ordered? So let's call this D. That's the distance between the base of the tower and where the guy wire hits the ground. The length of the base of our triangle. And we've got W for wire. What we're finding out is the length of wire needed, okay, in order to make this happen. Now, again, I'm in a right angle triangle. That means I can use my ratio, my tan ratio that I know. And I'm looking from, oh, they gave us an angle. So right away I'm thinking, sweet, here's the angle that I'm looking from, which means I have opposite, I have adjacent. Oh boy, but I actually need the hypotenuse. Is that a bit of a problem?
Nope.
No.
Why not?
Because we have the tan.
Because I have another tool in my toolbox. It's Pythagorean Theorem. A squared plus B squared equals C squared. Okay? Guess what? Tomorrow you're going to get a new ratio that will allow you to do this right away. Without getting D, you'll just be able to go straight, use 30 and 65 and get W. It's just a different ratio comparing different sides of a right angle triangle. But today we don't have that, so we have to do it in 2 steps. We're going to first write our little formula that we use. The tangent of, what do you want to call this angle?
C.
It's angle C, sure. The tangent of C is up over edge. I know angle C is 65 degrees. I know the opposite is 30. Adjacent is D. Last time we did this, my variable was at the top. That was a lot easier. Now the variable's at the bottom. I don't actually really know how to solve things with the variable at the bottom. Okay, I could do a little division triangle, if you remember division triangles. But I'll just show you algebraically how to do it first. Here's what you guys often do, students often do, I shouldn't say you guys, but generally here's what people do. They say, 30 divided by D, I better multiply both sides by 30. And all that's going to do is give you 900 over D. Just as useless. So I actually have to do this in 2 steps. In order to get D out of the denominator, I need to multiply both sides by D. On the left, that gives me D times the tangent of 65. And on the right, it leaves me with just 30. Now how do I get D?
You divide both sides by tan 65.
Divide both sides by the tangent of 65. Remember, the tangent of 65 is just a number. A couple examples ago, we typed stuff like that into the calculator and we just got a number out. So just don't think of this as anything confusing or long or multiple steps. It's literally just a number. It's the ratio of the opposite over adjacent sides in a triangle that has an acute angle of 65 degrees. That's all it is. It's the ratio of this number over this number. Okay? So divide both sides by the tan of 65. On the left, that will leave you with just d. And in your calculator, you might have to be a little bit more careful punching this one in. Clear, clear. 30 divided by, not really, if you just hit tan 65, 30 divided by the tangent of 65. Get it without a glare. Boom, there it is. Hit enter. Your calculator's smart enough. You get 13.989. We're going to round that up to 14. Okay? We're going to round that up to 14. And that gives us the distance away. We'll keep this answer, but it's actually, we're not going to use it.
Isn't it approximately 14?
Yeah, it is approximately, but that's exactly why we're not actually going to use this answer, because D is exactly 30 over the tangent of 65, and we can actually use this answer in our next section. Sorry, how did you say that the side lengths of a right angle triangle relate to one another?
Give me a second.
Pythagorean Theorem?
Oh, a squared plus b squared equals c squared.
Yeah, Pythagorean Theorem. So we've got w squared, which is our hypotenuse, is w, is going to be equal to d squared plus 30 squared. Can we agree on that?
Yeah.
All right. Well, we know that d is 30 over the tan of 65. Again, when you're replacing something, don't forget that d is that. So that still has to be squared. 30 squared is 900. I can put that in right away. That one I can do in my head. And I'm going to do something tricky here, because we don't care what w squared is. We want w. What did I do to the left side to get from here to here?
You square root.
I took the square root. So I actually have to take the square root of the whole right side as well. Now this might be a little bit trickier to put into your calculator, but you can do it all in one step, okay? So pay attention for a sec. We're going to go square root, and that's going to open a big bracket, okay? You can see how that opened a bracket. Now the rest of what we have we need to put in there, but this group is going to get squared, but I need to keep it as a group. So what I need to do is actually open another set of brackets, okay? Now I've got square root symbol, bracket, bracket. I'm going to go 30 divided by the tangent of 65. Now when I hit that tangent button, look what it did. It opened another bracket. So I need to close that bracket. Then I'm done this group, so I need to close that bracket. And now I need to raise it to the power of 2. I'm all still in my calculator. I'm inside the square root bracket. That's good, because I now need to add 900.
How did you raise it to the power of 2?
The x squared button right here. X squared button will raise things to the power of 2.
Right.
And now I need to close off that final bracket. And if I did it correctly, I should just be able to hit enter and it will calculate it all at once for me. It did. I got 33.1. Now,
490.
I got 33. I got error.
33.1. So I'll come around and help you with calculator stuff as needed. But for now, we'll just carry on. The measure then of the side length W is approximately 33.1 meters. Now, by not rounding this answer, by not using 14 in here, okay, we actually got a much more accurate answer. We didn't round at all. We got an exact answer, and then because our calculator has to round an infinite decimal, we rounded to one decimal place. Basically, the length of W needs to be 33.1 meters. And we're told that the wire can be ordered in whole number lengths. So how much wire should he order?
I have 33.2 meters.
In whole meter lengths.
Oh, 34 meters.
Yeah.
Does
Yeah.
the dot have to be there if it's not approximate?
So this is an exact answer. We don't need an equal sign with a dot. This is an approximate answer. It's been rounded. Yes, you must have a dot. Okay, now we're starting to do that. Yep, so this is an exact answer, no dot. This is a rounded answer because my calculator actually punched out 33.101333757. I'm cutting off all that extra information down in the thousandths and 10 thousandths and 100 thousandths and rounding it. So this is not exact. Not exact. So I need this. We should order at least 34 meters of wire. He should probably order more than that because undoubtedly he's going to have to make a bit of a loop on each side and clamp it closed. Or he might make a mistake, or he might need extra to pull on. I don't know if he's going to pull it by hand or if he's got a tractor or a come along or something like that.
Honestly, I would
They're gonna have more than us.
just get
Anyway.
rope and just kind of
Simple little thing here. If you want to see, I'll just draw this division triangle out a little bit here. And this works the same with anything in the world. So for instance, I'll do a really easy one right off the bat. If you have 6 divided by 2, what's the answer? 6 divided by 2 is 3. 6 divided by 3 is? 2 times 3 is?
6.
See how that works?
Yep.
Okay. Now, let's draw another one. Okay. Here I have d equals 30 over the tangent of 65. Or let's go up here actually. Because tangent of 65 equals 30 over d. So 30 is at the top. D is here. And they equal tangent 65. So the tan of 65 goes here. Not 65, the tan of 65. So we wanted to find d. We had to do a 2-step algebra process just to find the fraction that represents d. Look what my division triangle says. It says that if 30 over d is tangent of 65, then I already know that d times tangent of 65 is 30, which is what we did in our next step right here. And I know that 30 over tangent of 65 will get me d. Right there in your division triangle. If you know how those work, I can just look at this and I can say, oh, if 30 divided by this is that, then 30 divided by this is d. Just like you could do it here. If 6 divided by 2 is 3, then 6 divided by 3 must be 2. Same thing. Okay?
Oh,
So that's a real easy way to get from here to here. Plug that into your Pythagorean Theorem. Carefully use your calculator, and you get the length of that guy wire. Your practice problems for lesson 7. Is this 7.3? 7.3 come from page 330. You're responsible for numbers 1 through 12. Enjoy.
we will.